Alright, let's do this. Okay, so like I said, first question is going to be about dynamics, which is you have acceleration, and the next two are going to be about statics, where you don't have acceleration, okay? That means the forces are in equilibrium. So, in this scenario, could be like, you're sitting in your car and you're watching something hanging from your mirror, and you accelerate. It looks like the thing is moving backwards. So it looks like there's an angle to it. So it kind of looks like there's some sort of a force that is actually pushing. How many of you have ever seen like something, in your rear view mirror that's hanging from your rear view mirror? It looks like it's being pulled back. Well, there really is no force that's doing this. Actually, where is the force? Where is the force? You have something hanging from your rear view mirror, right? So it's just hanging like this. So here it is. It's just hanging. And then the car accelerates forward, so it goes this way. This thing looks like it swings back, right? So it kind of looks like this. But there is no force pulling this way. Where's actually the force? Where is it? Okay, let's think about it. You're sitting in a car, so you're watching this thing hanging from the rear view mirror. The car goes forward. This thing looks like it swings back. Now, by the way, I'm saying it looks like it swings back, because it actually doesn't swing back. It is inertia. This wants to stay in the same position. The force is actually up here, because this thing is being hung from the top of the rearview mirror, so the force is being experienced up here. So it's an illusion. This part is accelerating. Now, because this is accelerating and there is a downwards force because of the what? The weight? Then this is what it looks like. Looks like this. Now, we can make it totally symmetrical. We can make it look like a box. But this is the idea. So, how do you figure out the force of acceleration? Okay, so if we knew the angle, so let's say this angle was 30 degrees, then how would we figure out what this force is? Well, that's easy. We know what this is. We know the acceleration this way is what? Yeah. We know it's 9.8. So what would this be? What could you use? Yeah. We know tan theta is opposite over adjacent. How's the red working out? Okay? Red's okay? So that's going to be 9.8 over x. So tan 30 divided by 9.8 is equal to x. So I just flipped x with 9.8. So what do we get for x? So tan theta is 9.8 over x. So if I, whoops. Yeah, sorry. I apologize. Sorry. You're absolutely right. So we flip these two. This x is equal to 9.8 over tan 30. Sorry. Yep. Okay. What is that? What do we get for x? What is it? 17? Can't be.
Yeah, 17.
I guess it is. Yeah, okay. What did you say it was? Sorry? 17. Alright. No, it is. Yep, okay. That's right. Don't know why I thought it wasn't. That's right. Guess it just seems kind of like a big number, but this is a fictitious question, so. Alright, so that's how you would solve it. So that bonus question I gave you, that's all you have to do. Just use trigonometry. Figure out what the acceleration was. You want to kick yourself now? That's okay. Alright, that's dynamics. We have a net acceleration in this case. The next two questions I'm going to show you are have to do with statics. That means that the object is not accelerating. So we're going to use some concepts we learned in grade 11 to be able to solve the next two questions. Okay? So let's move on. Or should I pause and wait? Yes? No? Move on? Okay. So here's the next question. This is a question that's similar in your textbook. It's about a rock climber. So this is my rock climber over here, okay? So the person is, I should have got a better picture, pulling on a rope. Okay? So the person is pulling on a rope, and it says that there's a tension in the rope that is this way. Okay? The tension on a rope is 600 newtons, and it's 30 degrees below the horizontal. So this is 30 degrees. Okay? So tension's going this way. Tension is a force. Now, so this is my rock climber. This little line represents the rock climber's feet pushing on the side of the wall. So really it would look something like this. So here's my wall. Here is my rock climber. And his feet are actually on the wall. So there's the tension going this way. There's the force on the wall going this way. Okay? Now, there's another force that we could draw, which is this. That would be what? What would that have to be? So this is the tension. What would this have to be? This has to be the weight. Now there is another one that we're going to figure out, which is the force of the cliff. The cliff itself is going to exert a force on the climber because you can see otherwise there's an unbalanced force to the right. So the cliff is going to exert a force to the left, but you see it's actually to the left and somewhere else. So the cliff is actually going to exert a force back as in Newton's third law, right? The rock climber is pushing against the cliff. Cliff is going to push back. The rock climber is pulling on the rope, which is attached to the cliff. Cliff is going to push back. So this is what we're going to do. And this kind of logic you're going to use for the rest of the course. If you know something is not accelerating, this is what we start with. The net force has to be what? 0. Now, that means the net force in the x direction and the y direction has to be 0. Okay? You can't argue that because it's not accelerating. So there is no net force. So this is what we're going to do. We're going to figure out what are the forces before we figure out the force of the cliff. So we're going to look at tension, and then we'll look at the weights. And then we'll try to figure out the cliff. Because we know all three have to add up to 0. So let's look at tension. Well, we know we can think of it as a triangle. we can look at this component and this component. So let's look at our tension in terms of the x and y. So let's resolve the x component. What would that be? So it's 600. So I should tell you that. The tension is 600. So it should be what? 600 times cosine 30. Okay, what does that give you? Should be 500 and something. 520? Okay, 520. And we'll just say to the left for now. Okay? There's also force in the y direction, which would be opposite side. So it's going to be 600 times sine 30. And that would be 300. 300 up. Okay? So far it looks like nothing that we've never seen. Looks like something that we've seen before, right? Nothing new. So this is our tension. We resolved it into these two components. Our weight, well, is only one component, right? There is no x component. It's just the same as the vertical because it's only pointing down. So that would be the weight of the individual. So that would be 60 times 9.8, which is 588, is it? 588 newtons. Okay, now this is where we start looking at the net force. We know the net force has to be 0. Okay, so let's look at the x component first. So the net force along the x has to be 0, which means we have 520 to the left. The weight has no bearing on the left-right, so the weight is 0 going left to right. We could just leave it out. Plus the force of the cliff, and that has to all add up to what? 0. So that means the force of the cliff, if we bring this to the other side, this becomes negative 520. Sorry. Now the negative 520 means it's 520 to the what? To the right, which makes sense. Okay, that makes sense. All right, so we've resolved the x. Now let's resolve the y. Again, we know it adds up to 0. We know there is, the tension is pulling up. So we know it's 300 up. But we know there's a weight. Which way would the weight act? It would act down. So this is down. So that would be negative. Plus the force of the cliff. Alright, so again, same idea. So 0 would equal the sum of these two, which is what? Negative 288 plus the force of the cliff. So if we bring this to the other side, the force of the cliff would equal positive 288. So now we have the force of the cliff in terms of the x and y direction. We know it's 520 to the right, and we know it's 288 up. Okay? So now what we can do is we can just finish it off. I'll just change this. So I'll finish it off over here. So the force of the cliff would be 520 to the right. Never give myself enough room. Let's do this again. So it's going to be 520 this way and 288 this way. So we could pause. Yep, that should be. I put the wrong direction down. Oh, this should be left. We put left as positive. Yes, you're right. Yeah, the tension is actually to the right, not to the left. This is to the right. It's pointing this way. So the cliff would actually be opposite way. So it would be to the left. Thank you. Okay. So that's to the left. Alright, so left and up. Okay, so what is the actual force of the cliff? So the sum of the squares, yeah, it should be automatic for you guys now. So it's the sum of 288 squared plus 520 squared. What is it? Five, 594. Okay. And we should always get an angle. Some of you forgot that on your quiz. Opposite over adjacent. So what's the angle? 288 over 520. Take the inverse tan. What's that? 29 degrees. So then our final answer would be the force of the cliff would be 594 newtons left, 29 degrees up. Okay? So that's an example of a statics question where the big idea here is, remember, the net force is what? 0. Because it's not moving. So I'll show you one last example of net force being 0, because it's static, and then we'll end there, okay? So one last example. Sorry about that. So are we clear what will happen here? I pointed I made it go the wrong way. So tension's going right, according to this diagram, and I put left here by accident. So the cliff is going left, okay? Alright, last question. Alright, something hanging from the wall. So we have something hanging from the wall, and let me give you the angle. We'll say this is 45 degrees, and we'll say this, say it's 60 degrees. Okay, so I'm making the angle with respect to the ceiling. So imagine we have an object being, like maybe this could be a sign, being held from the ceiling. There are two cables attached to it. One cable, we'll call this one cable 1, is at an angle of 45 degrees. The other cable is at an angle, called cable 2, is at an angle of 60 degrees. And what we're going to do is we're going to figure out the force in cable 1, and we're going to figure out the force in cable 2. Okay? Alright, that's what we're going to figure out. Okay. So, change the color here. First, with any question with forces, you got to think about what are all the forces acting on this object. There's 3. Which way would this cable pull? Left and down? Pull. Left and up. Right? Which way would this cable pull? Right and up. Okay. We're missing one other force. Weights. Alright. So let's start with this. What must the net force be in the y direction? What must it be? Is this thing going up? Is it going down? Sorry, I shouldn't say that, because if the net force is 0, it could be moving up and down. Is it accelerating up or down? No. What's the net force in the x? Is it moving left to right? Is it accelerating left to right? No. Okay. So let's think about the y direction. Okay, let's think about the y direction. So let's look at the y. We know the net force is going to be 0. We know it's a sum of 3 forces. This one, cable 1. Now, how would you write it? Would it be just write it as cable 1, or would it be a component of cable 1? It would be. It would be which component? This component, right? So this, what could we write it as? We could say it's F1 sine 45. Now, this over here, it's also the vertical component for the second cable, but it would be F2 times sine 60. These two pulling up have to be equal to what? The weights, which we know is mg, which is 10 times 9.8. So we know that these two have to be equal to the weight. And the whole thing has to add up to what? To 0. Okay. What about the x component? We said that its net force is what? 0. Which means this cable is pulling which way? Left or right? Left. This one's pulling right. They have to what? They have to equal. Very good, Chloe. They have to cancel out. So we could say this. We could say cable 1 times this component, which is cosine 45, minus cable 2 and this component, which is F2 cosine 60, have to equal what? 0. Now, what you can do, and this is a skill that you're going to probably use many times in this course, is substitute. You're going to substitute. Okay, you're going to see this a lot actually. This skill of substituting one into the other. So this is what we can say. We could say this. We could say that F1 cosine 45 is equal to F2 cosine 60. They're equivalent to each other. So now, what do you think we could do here? We could do this. We can go back to this equation, we can substitute. Because we know what F1, we know the relationship between the two, we can substitute. So if we go back to this equation over here, we could say F1 sine 45 plus F2 sine 60. But F2 would be equivalent to, if I get rid of the cosine 60 on this side, F2 is the same as F1 cosine 45 over cosine 60. So I can substitute F2. I can say, okay, well, F2 is F1 cosine 45 over cosine 60 times sine 60, and that has to equal the weight, or 98 newtons. This will just leave us with F1 now, right? So F1 times sine 45 is, we can actually factor out the F1, can't we? We can do F1 is sine 45 plus cosine 45 over cosine 60 times sine 60 equals 98. And then if you want, we could divide all of this on the other side, or you can just go ahead and work it out. What is sine 45 plus cosine 45? I leave it up to you how you want to do it. Let's just work it out. What's sine 45? 0.71. Cosine 60 is what? Isn't it 0.5? Sine 60 is 0.86, right? Okay. So let's add all this up. What's 0.71 plus 0.71 times 0.86 over 0.5? Should be close to 1, I would imagine, the answer. What is it? 1.9? Okay, now get rid of the 1.9. So what's F1? Should be close to 49 then. What is it? So we'll just say 52. Okay. And now we have F1. So if we have F1, we could solve for F2. Because we know the relationship between them. We know F2 is F1 cosine 45 over cosine 60. We know it right here. So we can go ahead and solve for F2. So it's 52 times cosine 45 is 0.71 over cosine 60, which is 0.5. So what do we get? Should be about 70. 70, 74. Okay, so let's see if this makes sense. We have F1 is 52, F2 2 is 74. So this was 52. And this one, oops, is 74. Okay, this one's 74. Now, this makes sense because which string is more vertical? This one. So you would imagine that this is the string that's going to bear most of the brunt. So there's more tension in this string. This one is more on an angle. So this does actually make sense. Okay? Alright, that's it. That's how you do statics. Okay? Remember the big idea is net force equals, Kiara? Net force equals 0.